Swayam Prabha. Digital India. Educated India.
In our last class, we have seen different types of problems of dimensional synthesis of linkages. Today, we will get into the details of the geometrical method of solving these problems. We will start these problems with reference to a 4R linkage. First problem we discuss is that of motion generation. By motion generation, we mean how to guide the coupler of a 4-bar through various specified positions. First, we discuss the simplest problem of two-position synthesis. That means the coupler has to be moved from position 1 to another prescribed position, say number 2. This two-position synthesis can be, as I said earlier, without any coordination with the input movement. That means we are satisfied so long the coupler takes up the prescribed positions numbered 1 and 2, and we are not bothered what is the corresponding movement of the input link. Then we shall discuss how to solve the same problem of two-position synthesis coordinated with the input movement. In the second type of problem, as the coupler moves from position 1 to position 2, it is desired that the input link should be moved by a prescribed amount, say theta 2. After solving this problem, we get into three-position synthesis. That means the coupler has to occupy three specified configurations, namely 1, 2, and 3. Here, of course, we will discuss without any coordination with the input movement. That means we are happy so long the coupler passes through these three positions, and we are not bothered about what is the corresponding movement of the input link. Under this heading of three-position synthesis without coordination with the input movement, we can classify the problem into two headings. One is determination of fixed pivot locations. That means we shall choose the moving hinges A and B on the coupler AB, and we have to determine what must be the locations of the fixed pivots, say O2 and O4, so that the coupler passes through three prescribed configurations. Next, we shall discuss that given the fixed pivots, how to determine the location of the moving hinges on the coupler. This second problem is very often more important from practical considerations, because as we know, the fixed pivots have to be located on the frame, and if they are left unknowns, maybe those locations of the fixed pivots come at very uncomfortable or unsuitable positions. So we choose the fixed pivot locations on the frame according to our convenience, and we determine rather the locations of the required moving hinges on the coupler A and B. So let me start with the first problem, namely two-position synthesis without and with the coordinated input movement. To explain the geometric method of solving a two-position synthesis problem, let us consider this diagram. Here, the first position of the coupler, which is a rigid body, is defined by these two axes, say zeta 1 and eta 1. These two axes completely defines the position of the coupler, and that is what we call the first position 1. And it is desired that this coupler should move from this position 1 to position 2, and the corresponding positions of these two axes takes up eta 2 and zeta 2. That is, we have to design a 4R linkage such that by moving that linkage, we will be able to transfer the coupler from position 1 to position 2. And right now, we are not interested in the corresponding movement of the input link. To solve this problem, the first step is to choose location of A and B perfectly arbitrarily in this first configuration. Let us say A and B are the locations of the moving hinges on the coupler, and they are chosen arbitrarily. In the second position, the corresponding movement of A brings it to A2 and B goes to B2. As we must notice that the locations of A and B are fixed on this coupler. This is in position 1 A and B. In position 2, the same 2 points are here as A2 and B2. So the only job left is to determine the fixed pivot locations, namely that of O2 and O4. What we do, I know the length O2A remains constant, so A and A2 must lie on a circle with the center at O2. Similarly, the points B and B2 must lie on a circle with center at O4. So what we do, we join A1, A and A2, B and B2. Draw the perpendicular bisector of these two lines, namely AA2 and BB2. So we can choose O2 and O4 on these two perpendicular bisectors respectively. Anyway, if I choose O2 here, then O2A will be same as O2A2. That means by rotating the link O2A, it will come to position O2A2. Similarly, if I choose O4 anywhere on this perpendicular bisector, O4B will be equal to O4B2. So by rotating the link O4B, B will be moved to B2. So that is the simplest solution of a two-position synthesis without any coordination with the input movement. Now suppose we have also specified that as the coupler moves from position 1 to position 2, the corresponding movement of the input link, say O2A, must be theta 2 in the counterclockwise direction. Then in the previous solution, where O2 could have been anywhere on this perpendicular bisector, now the location of O2 is specified. To make this angle theta 2 between O2A and O2A2, what we do, we draw here at the point A a line at an angle pi minus theta 2 by 2, and that line intersects the mid perpendicular bisector which was drawn earlier at O2. So that decides the location O2. So now if this 4-bar linkage, namely O2A-B-O4, is moved, then as O2A rotates through an angle theta 2, the coupler will move from configuration 1 to configuration 2. It is very easy to see from this triangle that this angle is pi minus theta 2 by 2, so will be this angle, because O2A is same as O2A2, so the third angle will be theta 2, such that the sum of the three angles of this triangle comes out as pi. So this is the solution for two-position synthesis coordinated with the input movement. O4 can be still taken anywhere because we are not interested in the movement of the output link, namely O4B. Now, if we want to add another third position as 3, suppose I want a third position, we call it 3. Then A2 goes to a specific location, say here, which I call A3, and B2 goes here, which I call B3. So once we have chosen A and B arbitrarily on the coupler, then I know A, A2 and A3 must be on a circle. Similarly, B, B2 and B3 must be on another circle. And the centers of these two circles should determine the location of the fixed pivot, namely O2 and O4. So it is very easy to draw a circle passing through A, A2 and A3, 3 points. Similarly, it is very easy to draw another circle passing through these 3 points, namely B, B2 and B3. That will uniquely locate the fixed pivots O2 and O4. Previously, we had drawn a perpendicular bisector of A2, which was this line, and now I have to draw a perpendicular bisector of A2, A3. And if these two lines meet at this point, that will determine the location of O2. O2 will be the center of the circle passing through A, A2 and A3. Similarly, we have to find the center of the circle passing through B, B2 and B3, and that will determine the location of O4. So this is the 3-position synthesis for the 4R linkage when the moving hinges A and B were chosen arbitrarily on the coupler and the fixed pivot locations O2 and O4 can be decided. But as I said earlier, more often than not, it is the location of O2 and O4 which are chosen according to the convenience, and we have to determine the desired location of the moving hinges A and B on the coupler. We shall solve this problem in the next step. So let me now explain how to determine the moving hinges on the coupler such that a 3-position synthesis problem can be solved with given fixed pivot locations. Towards this end, we shall use the principle of kinematic inversion. If you remember, in a mechanism, the relative movements between various links remains independent of kinematic inversion. What do you mean by kinematic inversion? That in the same mechanism, we use a different fixed link and the original fixed link is allowed to move. We are interested only in the relative movement between various links, and the kinematic inversion leaves this relative movement untouched, independent of whichever link we hold fixed. So to determine the moving hinges on the coupler, we consider the same relative movement between the coupler and the fixed link, but we hold the coupler fixed and allow the original fixed link or the ground link or frame to move. We shall now explain this with the help of an example. Let the 3 positions of the coupler are prescribed by eta 1, zeta 1, this is position 1. These coordinate axes are fixed on the coupler. The second position of the coupler is given by position 2 when this eta, zeta takes up the position eta 2, zeta 2. Similarly, this is the third position with eta 3, zeta 3. The problem is that if we choose the locations of the fixed pivot at O2 and O4, where should be A1, B1, that is the moving hinges in the first configuration, such that as we move this 4R linkage, the coupler moves from position 1 to 2 and then from 2 to 3. To solve this problem, as I said earlier, we shall use the principle of kinematic inversion. To locate A1, B1, what we do, we fix the coupler at this first position and let O2, O4 move, keeping the same relative movement as prescribed here. So let me do this inversion by using a tracing paper. I use a tracing paper and put it here and draw this eta 2, zeta 2, and the position of O2 and O4 I mark on this tracing paper. So I have drawn this eta 2, zeta 2 axis on the tracing paper, as you can see here, and mark the position of the fixed pivots, given fixed pivots O2 and O4. The same relative movement I consider as if the coupler has not moved from the first position. That means this is the position of, I coincide eta 2 with eta 1 and zeta 2 with zeta 1. So the second position, if I hold the coupler fixed in the first position, then O2 and O4 move to these two positions. This is O2, this is O4, having the same relative positions in the second configuration. But I have fixed the coupler in the first position. These two positions we mark on the paper by piercing with a point. So this is the position of O4, this is the position of O2. I name these positions as follows. I call it O4 in the second configuration, but inverted on the first configuration. So I call it O4, 2, 1. This is really, I could have said, this is O4, 1, 1. And this is O2, 1, 1. So holding the coupler fixed in the first position, if I allow the fixed link to move, then O4 comes here and O2 comes here. This I call O2, 2, 1. I hope it is clear that how I get the inverted position of these two fixed pivots if I hold the coupler fixed in the first position. Then we take the tracing paper again, draw eta 3 and zeta 3 and mark this O2, O4. I mark it by putting a cross. So this is the relative position of O2, O4 with respect to the coupler in the configuration. If I make a kinematic version with the coupler fixed in the first position, that is eta 3, zeta 3, I make coincide with eta 1 and zeta 1 respectively, then O4 moves here and O2 moves here. So this position I called O4, the third position, inverted on the first position. Similarly, this is O2 in the third position, inverted on the first position. So if we fix the coupler and allow the fixed link to move, the same relative configurations as given by the moving coupler with respect to the fixed link, then the fixed link moves such that O2 goes from O2 to O221 to O231. Similarly, O4 goes from O411 to O421 and O431 by holding the coupler fixed. If the coupler is fixed, then A does not move, A is fixed, and because A O2 distance is same, then O2 moves on a circle with A as center. So we have to determine the center of the circle passing through these O21, O22, O211, O221 and O231. This is 1 point, this is 1 point, and this is 1 point. So it is very easy to determine the center of a circle passing through these 3 points, and that will be A1. Similarly, the center of the circle passing through O411, O421 and O31. This circle, the center of that circle will be, say, here, and that will be B1. So now we have located the moving hinges, required position of the moving hinges, such that if O2, A1, A1, O4, these 4 are linked, is moved, the coupler goes from position 1 to position 2 to position 3 with O2, O4 as the fixed pivots. As the principle of kinematic inversion forms the basis of this procedure for dimensional synthesis, let me repeat it once more, the solution shown in this figure. What we have done, we are using a tracing paper, eta 1, zeta 1, eta 2, zeta 3, zeta 3. They specify the 3 positions, desired positions of the coupler. O2 and O4 have been chosen according to the convention. Our task is to determine the location of the moving hinges A and B. Say we want to decide it in the first position of the coupler. We make a kinematic inversion, hold the coupler fixed in its first position and allow the fixed link to move, and determine where do these points O2 and O4 go to keep the same relative movement between the coupler and the fixed link, which remains invariant for a given mechanism. Now you note O2 I call O211. This subscript 1 refers to the configuration and the superscript 1 refers where we are inverting. That means which position we are holding fixed. So the superscript in this problem will be always 1 because we are always inverting on the first position which we are holding fixed. So let me explain how do I get these inverted positions. What we do, we use a tracing paper and mark this second configuration defined by eta 2 zeta 2 axis, and the relative position of this fixed pivot in the second configuration, here is O2, here is O4. So if I now have the same relative movement but hold the coupler fixed in its first configuration, that means eta 2 zeta 2 I coincide with eta 1 zeta 1, and you see the O2 moves here, O4 moves here, such that the same relative position corresponding to the second configuration is maintained. So O2 comes here, O4 comes there. This position I call O2 2 1 and this position I call O4 2 1. Again you note superscript 1 refers to the configuration 1 where we are fixing or holding the coupler fixed, and this 2 refers to the configuration which is being inverted. It is the second position which we inverted. For the third position, we draw on the same tracing paper eta 3 zeta 3 and mark this O4 and O2. Now the same relative position between the coupler and the fixed link is maintained, but the coupler is fixed in its first position. So I move this and make it coincide eta zeta with eta 1 zeta 1. And as we see, O2 moves here, the O4 moves there. So this position I call O2 3 1 and this position I call O4 3 1. Now rest is simple. I determine the center of the circle by drawing these two perpendicular bisectors of O2 1 1, O2 2 1 and O2 2 1 and O2 3 1. These two perpendicular bisectors intersect here, which is the center of the circle passing through these three inverted positions of O2, namely O2 1 1, O2 2 1 and O2 3 1. This is what I call A. Similarly, the center of the circles passing through the three inverted positions of O4 is B, and that is the other moving hinge on the coupler. So the problem is solved that O2AB04 is the required 4R linkage, which when moved, the coupler moves from position 1 to position 2 and position 3. This is the 3-position synthesis of motion generation for the coupler of a 4R linkage with the fixed locations of the ground pivots. Let us now take an example of this 3-position synthesis with reference to this tipper dumper. As we see here, the dumper bin, that is link number 3, is driven by this link number 4, which is driven in turn by this hydraulic cylinder piston arrangement, which are link number 5 and 6. So as this cylinder expands, this link 4 turns clockwise, and here we have a 4R linkage, namely O2 A B O4. This 4R linkage is driven by moving link 4 by this hydraulic cylinder, and as a result this dumping bin goes from this configuration to some other configuration and the final dumping configuration. our job is to locate the suitable positions of A and B for given locations of O2 and O4. These are the fixed pivots which must be on the body of this tipper dumper, and A and B have to be determined such that this dumping bin passes through 3 given configurations. That is the problem, and let us see how do we solve it by this principle, using this principle of kinematic inversion. So let us now discuss this example of the tipper dumper, and the dumping bin has to take up this first configuration, which is the configuration during the transporter movement. This is another configuration which we call the intermediate configuration, and this is the third configuration which I call the dumping configuration. So the task is, for given locations of O2 and O4, we have to determine where should A and B lie on this dumping bin such that when you move this 4R linkage, the dumper goes from transport to intermediate to dumping configurations. The thing to note that in plane motion of a rigid body, the configuration of the rigid body is completely defined by any 2 points on it. Here we take those 2 points as this corner x1 and this corner y1. So we can forget about the rest of the dumping bin, and we only concentrate on these 2 points, namely x1 and y1. That is, their locations in the first configuration, then x2, y2, that is their locations in the intermediate configurations, and x3 and y3, their positions in the dumping configuration. So the dumper bin is completely defined by x and y, passing through these 3 positions x1, x2 and x3, y1, y2 and y3. As I said, I will make a kinematic inversion to locate A and B in the first configuration, that is transport configuration. We hold the dumper bin fixed in this first configuration. That means x1, y1 will not move, rather we allow O2 and O4 to move, keeping the same relative movement. That is kinematic inversion. To carry out the inversion, I use a tracing paper and mark this point x2 and y2, and mark O4 and O2, O4 and O2, x2 and y2. If we hold the dumper fixed in first configuration, then we make x2 coincide with x1 and y2 coincides with y1. And we see that this O4 has moved to this position and O2 has moved to this position. So these 2 positions we call O2 21 and O4 21. This is O4 21, this is O2 21. To invert the third position, we mark x3 and y3, and also O2 and O4. Now if I invert it on the first position, that is x3 goes to x1 and y3 goes to y1. And as we see, this O4 has come here, which I call O431, and O2 has come here, which I call O231. Thus, we have located the 3 inverted positions of O2, namely given location, which is O211, and these 2 inverted positions O231 and O221, and similarly for O4, the given location O4, which is O411, and the inverted positions O421 and O431. So the center of the circle passing through these 3 inverted positions of O4 determines B, and the center of the circle passing through these 3 inverted positions of O2 determines A. So if I join O2A and O4B, we get the required 4R linkage, which will drive the dumper bin through these 3 configurations 1, 2 and 3. So we have just seen how to solve the problem of motion generation for 3 position synthesis. We have noticed that the whole method depends on the fact that 3 points lying on a circle has a unique center. So, if we want to extend this method to more than 3 accuracy points, what happens? You remember what we did? Suppose we wanted to locate the fixed pivots after choosing the moving hinges A and B. We use the fact that A moves on a circle with O2 as center. So, A1, A2, A3, 3 positions of the point A determines O2 as the center of the circle passing through A1, A2, A3. Similar thing is true for the location of O4, which is the center of the circle passing through 3 positions B1, B2, B3. Then the question is, can we extend this method to more than 3 accuracy points? Because then A1, A2, A3, A4, which are all 4 arbitrary positions, there is no guarantee that they will lie on a circle. So, there is no way we can determine the center. However, there is a method which is beyond the scope of this course, so we will not discuss the detail, but you can think of that there must be a solution if you keep the following fact in mind. You see, the location of A was perfectly arbitrary. I could have taken A anywhere on the plane of the coupler. So, there are special locations of this point A such that as the coupler moves through 4 arbitrary positions, A will lie on a circle. So, this method can be extended to even 4 accuracy points. In this course, we will discuss some limited version of this by saying using a method of point position reduction that we will take up much later. The method can also be extended to 5 position synthesis, but then A cannot be chosen arbitrarily. For 3 positions, A was chosen anywhere on the coupler plane, so is B chosen anywhere on the coupler plane. For 4 position synthesis, A have to be chosen on a particular curve. For 5 position synthesis, there are only some discrete fixed locations for the choice of A. As I said, this general discussion of 4 and 5 position synthesis is beyond the scope of this course. We will discuss later on some limited version for 4 position synthesis by a technique which is known as point position reduction. At this stage, let me now get into the second type of problem, namely the problem of path generation. For path generation, we start our discussion with 3 position synthesis, because 2 position synthesis, as we have seen, is pretty obvious. For 3 position synthesis of path generation, the problem is posed as follows. Let a particular coupler point C has to pass through 3 positions, namely C1, C2 and C3. Actually, this is the desired coupler curve, but we are not interested in the intermediate positions. We have defined a 3 position synthesis problem that a coupler point C of a 4R linkage must pass through C1, C2, C3. To solve this problem, we choose O2 and O4, the location of the fixed pivots, arbitrarily anywhere according to the convenience of the problem. Then we also choose A1 arbitrarily. A1 is the moving hinge on the input link. The only thing remaining is to determine where is the other moving hinge on link number 4, which I called B, that is B1. O2, A1, B1, O4 is the required 4R link, and the A, B, C is the coupler. So, as this 4R linkage moves, this particular coupler point C should pass through C1, C2, C3. And we have to determine where must be the location of the other moving hinge B1. To do this, we again make a kinematic inversion. As we see, we have to determine the point B on the first position of the coupler, that is ABC, B1. So, we hold the coupler fixed in its first position and allow the fixed link O2, O4 to move. Since B1 remains fixed and B1 O4 distance is constant, so O4 must move on a circle with B1 as the center. So our job is to determine what we call the inverted position of this moving hinge, fixed hinge O4 as O4, which we called O4 1 1. We have to determine O4 2 1 and O4 3 1 corresponding to the 3 positions of the linkage. To do this, we proceed as follows. First, we determine the location of this moving hinge A corresponding to the other 2 configurations. As we see, because O2A distance is constant, A must lie on this circle. This is what we call the path of A, say KA. A lies on this circle with O2 as center and O2A1 as radius. Since the distance A1C1 is also fixed, this is one of the coupler lengths. So we determine A2 by making C2A2 as C1A1. This C1A1 is same as C2A2 and A must lie on this circle, so I can determine the location of the point A2. This I mark as A2. Similarly, corresponding to the third position, since AC distance remains constant, I draw a circular arc with C3 as center and CA as the radius, and that intersects the path of A at this point, which I call A3. So AC is one part of the coupler, ABC is the coupler. We have to determine B1 by holding the coupler fixed at its first position, that is at A1C1. We have to determine the inverted positions of this fixed hinge O4. So what we do on a tracing paper, we use a tracing paper and mark A2, C2 and O4. A2, C2 and O4. The same relative position is maintained, but at the first configuration. That means A2, C2 I make coincide with A1, C1. A2 with A1, C2 with C1, and as we see, O4 moves here. So we mark this point on our drawing sheet. This point we call O4 corresponding to the second position but inverted on the first position. We call it O4 2 1. Again, now we consider the third configuration, that is we mark C3 A3. I put across A3 C3 and O4. Let me now show how to find out the inverted position corresponding to the third configuration. So this is C3, I put it as a cross, and this is A3, and this is the location of O4. So if I invert it on the first position of the coupler, that means I make C3 coincides with C1, A3 coincides with A1. This C3 I am making coincides with C1 and A3 with A1, and as we see, O4 has moved there. So I mark this point on my drawing sheet, and this I call O4 3 1. So if the coupler is held fixed corresponding to these two relative movements or these three configurations, the location of O4 is here, here and here. If the coupler is held fixed at its first configuration, that is the point B does not move, it remains at B1 and O4 moves in a circle with O4B as the radius. So if I locate the center of the circle passing through these three positions, this is the circle which passes through these three inverted positions of O4 and the center is determined somewhere here, which I call B1. So we have determined the linkage O2, A1, B1, O4 and C is the coupler point and this ABC is one rigid body. ABC is the coupler, this is one rigid body and this is another link which I can join as another rigid link. So O2, A1, B1, O4 with C1 as the coupler point, and if this linkage moves as A1 goes to A2, C1 will take up the position C2, and as A2 goes through A3, C1 will take up the position C3. So we have solved the problem of path generation with three accuracy points. Let us now see at the solution of the problem which has been solved just now. As I said, C1, C2, C3 are the three required points of the path of the coupler point C. These are given to us. O2 and O4 have been chosen arbitrarily according to the convenience. We also choose A1 arbitrarily. The only point is to determine where should be B1, the other moving hinge. So what we have done? First, we determine the path of A, which is a circle with O2 as center and O2 A1 as radius. On the path of A, I locate the position of A corresponding to the second and third configurations as A2 and A3. This is easily done since I know this distance AC being a rigid link does not change. So with C2 as center, I draw a circular arc with AC as radius and that intersects the path of A at O2. Similarly with C3 I get A3. Now we make a kinematic inversion to locate the point B1. Please note that because we want to locate the point B1 which is on the coupler, I hold the coupler fixed such that B1 does not move and it is finally obtained as the center of a circle passing through 3 points. Now with B1 fixed, it is this point O4 which moves on a circle with B1 as center and B1 O4 as radius. To locate the inverted positions of O4, we have done as explained earlier. Let me repeat it. We mark A1, C1 and O4. This is the relative positions of A1, A, C and O4 in the first configuration. So I call this O4, O4, 1, 1. Corresponding to the second configuration, the relative positions we mark A2, C2, O4. These are the relative configurations of the points A, C and O4. Now we are holding the coupler fixed. That means A2, C2 does not move, rather they remain at A1, C1. If they remain at A1, C1, as we see, this point O4 comes here, which I call O4, 2, 1. Similarly, we mark A3, C3 and O4. These are the relative positions of A, C and O4 in the third configuration. Because we are inverting on the first configuration, I take C3 to C1 and A3 to A1, and wherever O4 goes, that I call O4 3 1. So I hope this is clear how to obtain the inverted positions of O4, and the center of the circle passing through these three inverted positions of O4 is at B1, as determined by these two perpendicular bisectors. So we design the linkage O2, A1, B1, O4 with C1 as the coupler point, which if this linkage when moved, C1 passes through C1, C2, C3. Again I emphasize, please note this notation. O4 2 1, the subscript 2 refers to the second configuration which is being inverted on this superscript, that is the first configuration. Similarly, O4 3 1, it is corresponds to third configuration and inverted on the first configuration. I would suggest the students can try by inverting, say, on the second configuration rather than on the first configuration. That means you will locate the point B2 rather than B1. You say that the coupler does not move from A2, B2, C2, and you invert the first position on the second and third position on the second, when O4 will be O4 2 2, and the other two positions will call O4 1 2 and O4 3 2, and the center of the circle passing through these three inverted positions will locate B2. So let me now summarize what we have learned today. Today we have discussed the method, the graphical method for three position synthesis with reference to motion generation and path generation problem. We treated the coupler as the moving link, and for motion generation it is the position or orientation, that is the configuration of the coupler which were prescribed and had to be satisfied. In the path generation problem, it is a particular point on the coupler which had to take three positions which were specified, and we had to come up with the 4R linkage. We must have noticed the most important point of this graphical method is the principle of kinematic inversion. The student should note inversion should be done on which link, that means which link should be held fixed and on what configuration. We have a choice. We can choose the inversion to be made on the first, second or third configuration. It does not matter, but it is the choice of the link which had to be chosen depending on the problem. For example, in both motion and path generation problem, we had to hold the coupler fixed and allowed the fixed link to move. In our next lecture, we will discuss function generation problem, and we will see that we have to make a different kind of kinematic inversion to solve that problem.